Welcome to the first lecture. So today we are going to discuss why quantum mechanics. Why do we need it? The main motivation historically for quantum mechanics comes from the fact that at the end of 19th century, classical physics had a spectacular failure to explain a problem. So the problem was to calculate the radiation of a black body. So the problem was computing the black body radiation. And people tried to use classical theory of electromagnetism to explain the observed spectrum of the black body radiation, and they failed. So before we can discuss what a black body radiation is, we need to know what is a black body. So a black body as the name suggests, is a perfect absorber it's a perfect absorber of radiation, and that's why it's black. A black body is actually an idealization. In nature, we don't really have any perfect black body, but we can approximate a black body by the following contraption. So what we can do is that we can take a kind of metallic enclosure. So this is a box, and the box has a small opening on its side. Then what happens is that if a ray of light or some radiation enters this chamber through this little opening, then what will happen is that it'll get reflected inside and it'll bounce around. It'll bounce around, and the probability of this radiation getting out through this opening is very, very small. It's very tiny. And therefore, eventually, this radiation will get absorbed. So as you can see, this enclosure acts as a system which absorbs all the radiation that enters within this chamber. So this is how you approximate a black body. Now, if you heat up such an object, so if you put it on a, say, Bunsen burner, and if when the object is in thermal equilibrium, what happens is that it fills up with radiation. It fills up with radiation, and this radiation leaks out, through this opening, and this is what we call the black body radiation. And you can show on thermodynamics ground that the black body radiation, the spectrum of this black body radiation, does not depend either on the size or the material of the black body. So the radiation is independent of the size, the size and shape actually, and the material, as long as the enclosure is large enough. So this is how we can measure the black body radiation. Now what we can do is that we can do a spectral analysis of this radiation. So, and then we can draw a graph of what the spectrum of the blackbody radiation is. So if we observe this, and people observed that if you draw a graph where along the x-axis you put the you put the frequency of the graph, frequency of the radiation, and along the y-axis you put the intensity. So here, what we said is that the radiation is independent of the, shape and the material. And you can show from a general thermodynamic grounds that the radiation depends only on two things. One is the frequency. The spectrum depends on the frequency, and it depends on the temperature. So here we are assuming that when we heat this up, this is heats up to a very high temperature, but it is at thermal equilibrium. Okay, so there is no, like, the temperature here is equal to the temperature here, and so on and so forth. So we are assuming thermal equilibrium. So if you do that, then the observed spectrum that experimentalists found out was something like this. And probably, it went down something like this. So which is a very nice curve, physical curve. And then what people did is that they tried to predict this curve or derive this curve using classical electromagnetism. And the best result that they could get is known as the Rayleigh genes formula. And Rayleigh genes, let me write that down. It's two people, Lord Rayleigh and genes. So what Rayleigh genes discovered was, they were able to derive a formula which worked pretty well in the lower frequencies, but then it diverged. So according to the Rayleigh genes formula, the radiation coming out from the black body should be infinite. So this is not good. So see that this end of the spectrum is where we have the ultraviolet, and on this end of the spectrum we have the infrared. And because this formula, the Rayleigh genes formula, and any other attempt using classical electromagnetism failed at the ultraviolet end, this divergence was dubbed the ultraviolet catastrophe. Sounds like the name of a video game, but that's the name it was given. So the ultraviolet catastrophe was a spectacular failure of classical electromagnetism. And this is the reason why Planck came up with his quantum hypothesis, which we will discuss later on today. However, before we go on to derive the Rayleigh genes formula, I want to take a little detour and refamiliarize you guys with the definition of what we understand by averages or expectation values. So that's going to be our next topic.